What can we learn from the oceans of the past for today's climate situation? Ancient ocean slowdown warns of future climate chaos. Hello friends, Jim here. So what is going on? When it comes to the ocean's response to global warming, well, we can learn from the past, and we have. A UC Riverside study shows that episodes of extreme heat in Earth's past caused the exchange of waters from the surface to the deep ocean to decline. This system has been described as the global conveyor belt because it redistributes heat around the globe through the movement of the ocean waters, making large portions of the planet habitable. Using tiny fossilized shells recovered from ancient deep sea sediment, the study appearing in the Proceedings of the National Academy of Sciences demonstrated how the conveyor belt responded around 50 million years ago. Oh, what happened 50 million years ago? That was the PETM, hothouse Earth, right? Paleocene, Eocene, thermal maximum. At that time, Earth's climate resembled conditions predicted that will be the situation here for this planet by the end of this current century. Oceans play a crucial role in regulating Earth's climate. They move warm water from the equator toward the North and South Pole, balancing the planet's temperatures. Without this circulation system, the tropics would be much hotter and the poles much colder. Changes in the system are linked to significant and abrupt climate change. Furthermore, the oceans serve a critical role in removing anthropogenic carbon dioxide from the atmosphere. If the oceans stay cool enough for solubility to occur. The oceans are by far the largest standing pool of carbon on Earth's surface today, says Sandra Kirtland-Turner, Vice Chair of UCR's Department of Earth and Planetary Sciences and the lead author. Today, the oceans contain nearly 40,000 billion tons of carbon, more than 40 times the amount of carbon in the atmosphere. Oceans also take up about a quarter of anthropogenic CO2 emissions, which then increases the acidity of the ocean. If ocean circulation slows, the absorption of carbon into the ocean may also slow, amplifying the amount of CO2 that stays in the atmosphere. And also remember, we'll talk about, they mention this later on, as the oceans warm and stratification increases, solubility of CO2 drops off, but then productivity decreases, and then if productivity decreases, the amount of marine snow decreases. Marine snow are dead organisms that, as they sink through the water column, sequester carbon, called a biological carbon pump. Previous studies have measured changes in ocean circulation in Earth's more recent geologic past, such as coming out of the last ice age. However, those do not approximate the levels of atmospheric CO2 or warming happening to the planet today. Other studies provide the first evidence that deep ocean circulation, particularly in the North Atlantic, is already starting to slow. To better predict how ocean circulation responds to greenhouse gas-driven global warming, the research team looked to the early Eocene epoch between roughly 49 and 53 million years ago. Earth then was much warmer than today, and that high heat baseline was punctuated by spikes in CO2 and temperature called hyperthermals. Not hypo, hyperthermals. Right? Paleocene, Eocene thermal maximum is what they're talking about, PETM. During that period, the deep ocean was up to 12 degrees Celsius warmer than it is today. During the hypothermals, the oceans warmed an additional 3 degrees. An additional. That's on top of the 12. That's 15. Though the exact cause of the hyperthermal events is debated, and they occurred long before humans were here, these hyperthermals are the best analogs we have for future climate change, Kirtland Turner said. By analyzing tiny fossil shells from different seafloor locations around the globe, typically forams, the researchers constructed patterns of deep ocean circulation during these hyperthermal events. Right? Foraminifera, forams. They're found all over the oceans. Surface, seafloor, right? They're all over the place. They're not that big, about the size of this period here in this print here. But as the creatures build their shells, they incorporate elements from the oceans, and we can measure the differences in the chemistry of these shells to broadly reconstruct information about ancient ocean temperatures and circulation patterns. We are talking about isotopic fractionation. There are a number of fractionations that they can look at. The shells themselves are made of calcium carbonate. The chemical formula is CaCO3. You got calcium, you got carbon, you've got oxygen. Oxygen isotopes in the calcium carbonate are indicators of temperatures in the water that the organisms grew in. They can also tell us the amount of ice on the planet. So basically, you have there are 3 isotopes of oxygen, O16, O17, O18. 17 is extremely rare. So the major ones are 16 and 18. And even then, the amount of 18 compared to 16 is small. But when you form land ice, water molecules are H2O, right? Well, if you have a water molecule with the O18 isotope, that's a little heavier. That is less likely to go into the atmosphere to fall as snow on land that gets compacted into the ice. So in other words, more of the O18 is left behind in the ocean when you have ice sheets on the land. So we see this. You see a higher O18 to O16 in the forams. When you see that higher ratio, you know you have ice sheets on the land. And conversely, if you look at the ice sheets, the O18, O16 is much lower because basically it's diluted with the O16. So that's how you can use oxygen isotope, basically say, there was a lot of, a higher O18, O16 ratio tells me there was ice on the land, so the oceans were colder. A lower O18, O16 in the forams tells us less ice on land, warmer ocean condition. And if it's really, really, really low, then it's really, really, really warm in the oceans. Basically, what that tells us. They also looked at the carbon isotopes. And what they specifically look at is the C13 to C12 ratios. So by looking at that ratio, it reflects the age of the water where the shells were collected, or how long water has been isolated from the ocean surface. In this way, they can reconstruct patterns of deep ocean water movement. Now, I did a video several years ago now where I just explain in detail isotopic fractionation and how it's used to reconstruct past climate. I discuss in great detail O18, O16 ratios, C13, C12 ratios. I also did an addendum to explain the fractionation aspect to that. You may want to look at those two videos to help understand how isotopic fractionation works. Now, forams are not able to photosynthesize, but their shells indicate the impact of photosynthesis of other organisms nearby, like phytoplankton. Photosynthesis occurs in the surface ocean only, the photic zone. So water that has recently been at the surface has a carbon-13 rich signal that is seen reflected in the shell when that water sinks to the deep ocean. Conversely, water that has been isolated from the surface for a long time has built up relatively more carbon-12 as the remains of the photosynthetic organism sink and decay. So older water has relatively more carbon-12 compared to young or younger water. So a high C13 to C12 ratio indicates younger water or water that has been at the surface, whereas a low C13, C12 ratio indicates older water, or water that has been more isolated from the surface. Scientists often make predictions about ocean circulation today using computer climate models. They use these models to answer the question, how is the ocean going to change as the planet keeps warming? This team similarly used models to simulate the ancient ocean's response to warming. They then used the foram shell analysis to help test results from the climate models. And during the Eocene, there were about 1,000 parts per million, ppm, of CO2 in the atmosphere, which contributed to that era's high temperatures. Today, the atmosphere holds about 425 ppm, or I think I'm seeing recent measurements of 427. That's CO2. If you look at the ppm of equivalent CO2, it's much higher. However, humans emit nearly 37 billion tons of CO2 in the atmosphere each year. If these emission levels continue, similar conditions to the early Eocene could occur by the end of this century. And don't forget, as you warm the oceans, you get stratification. That also slows down the sinking, the deep water formation, adding to further warming and with the warming waters, any CO2 outgasses to the atmosphere, increasing the CO2 levels in the atmosphere, increasing the warming. So we can also use the C13, C12 to tell us when deep water formation was flowing or not, when heat and CO2 is being sequestered to depth or not. We can tell all that. So, very important work here, but once again, verifying, in essence, how good a technique, how useful a technique the isotopic fractionation method is, and helps us reconstruct what happened in the past and inform us of what is likely to come in the near future. And right now, it is not looking good for human survival and for many other species' survival. So there you have it. Thank you for your time. We'll talk soon.